Okay. Uh, Good day, everyone, wherever you're calling in, and good morning for people in the room. Welcome to the second day of George's meeting. Our first speaker today is Zdenek Prudil, so please, Zdenek, take it away.
Hello, everyone. Good evening from Shiraz. Good morning to Los Angeles. I hope that you are having a good time. Today, I'm going to talk about a project that was inspired by the work of George Preston, shocks in photometric light curves of fundamental mode RLR stars. This project is actually a pre-corona project. We already finished the work and published it in 2020. In this project, I worked with Radek Smolec, with Marcio Catalan, who is hopefully in the room, with Istvan Dekani, with my former PhD supervisor, Eva Grebel, and with Andrea Kunder. Now, let's start with something very easy on the start, or not easy, but I guess you're all familiar with RLR stars. I like this comparison to RLR stars to Swiss Army knife, which is very interesting and a useful comparison that somebody invented in our field. That RLR stars are very useful tools for many various astrophysical projects, ranging from stellar pulsation, stellar evolutionary models, toward the cartography or galactic archaeology and charting the structure of the Milky Way and its closest neighborhood. They're also useful metallicity indicators, so they have various numerous applications in astrophysics. There are, of course, different subtypes, and throughout this talk, I will be talking about this fundamental mode RLR stars, these very sawtooth shaped like light curves, the most numerous subtype. And in our field, we often try to sort of improve these individual useful features of RLR stars. And I think what could be in the future, particularly with the shocks, is that we could add a little bit more power tools towards RLR stars. Now, let's start with the shocks. Shocks in RLR stars have been observed more than 75 years ago. And they mostly affect the Balmer lines, or the strong line profiles, and they've been variously and extensively studied in the stellar spectra. Today, during this talk, I will be talking about mainly about early and main shocks, which are basically consequence of the pulsation mechanism, the collision of the atmospheric layers during the pulsation, where the early shock happens right before the brightness minimum, and the main shock, the very strong shock in the atmosphere, happens right before the brightness maximum. You see on these nice images from Gillett and Crow from 1988 that during the shock phases, during the pulsation, which are very short ones, for example, the H alpha is affected by emissions on the blue and red side. What inspired me to work on the projects related to shocks was actually a paper by George Preston in 2009, the observations of the helium emission and absorption lines in the spectra. And for me, that was a big surprise, because RLR stars have temperatures around 6,000-7,000 Kelvin, and suddenly you start observing lines of the helium. Of course, that's because of the strong energy of the shocks, but for me, this was a very peculiar discovery. And there was also a Preston and collaborators paper from this year, which they expanded on their previous study, which I particularly enjoyed, and I especially like the part where the data that they used is going to be public, or is public now, so we can start using it in our work as well. There is a multiple effects of the shocks on the lines in the spectra of RLR stars, particularly on the Balmer lines, their absorption, emissions, the line doubling, but also calcium and metallic lines are affected apparently during the main shock. Now, in the photometry, the main and early shock are characterized by these sort of wrinkles on the light curve that we call bump and hump. There are, of course, other shocks that have different names, like rump and jump. I'm not going to dive into those ones. I'm going to focus only on these very prominent ones that you can see in almost all of the light curves of RLR stars. You see this wrinkle right before the brightness minimum, that's called bump, and it's associated with the early shock. The hump right before the brightness maximum in this narrow part of the phase during the pulsation is related to the main shock. And when I sort of started looking at the shocks, and because I had some experience with the photometry in RLR stars, I asked myself questions like, are all the light curves of RLR stars affected in the same way of these shocks? are there any connection between the strength or prominence of the hump and bump with their pulsation properties? And do all of the stars have these wrinkles on the light curve? And are those wrinkles all the same? Because if you look at the light curve, they look quite consistent. And if you look at the different light curves, they might be looking quite differently. And in different wavelengths and different passbands, they would look differently. So in our project, we decided to study these photometric effects of the shocks. We selected a very ground-based photometric survey that provides a large amount of epochs, a large amount of photometric data. We selected the OGLA survey that charts and maps the most densest stellar fields in the Milky Way, particularly the galactic disk, bulge, and Magellanic Clouds. And for this project, we selected the LRS stars from their bulge project. We selected stars, LRS stars that are pulsating in the fundamental mode, that have that sawtooth shape like, and that doesn't show any additional modes or any kind of modulation. There are some of the earlier stars exhibit sort of a light curve modulation that changes the shape and amplitude during the pulsation. And we try to avoid using these stars in our analysis. We try to have the earlier stars that every pulsation cycle looks like the previous one. We also selected stars that have a large number of observations and that are sufficiently bright to sort of minimize the effect of the photometric errors. In the end, we ended up with a sample of roughly 1,500 LRS stars suitable for our study. This is their distribution in a period amplitude diagram. They roughly cover all of the periods and amplitudes in a semi-homogeneous way. Of course, we have the main Osterhoff-1 sequence here, but we are covering also the long period LRS stars. Since this was sort of a first study of its kind, we needed to develop an approach how to estimate the strength of the humps and bumps on the light curve, their prominence. And we started with a sort of obvious choice and started fitting the light curves of LRS stars using a Fourier series, which is a quite common technique in the LRF field. We first overfitted the light curve with a high degree of the Fourier series to sort of describe all of the little wrinkles on the light curve. In the next step, we chose the region where the hump was occurring, and we removed it. We removed the sort of the feature. If you look at it from the spectroscopical point of view, we tried to fit the continuum, but we removed the line, sort of not fit the line as well. So we removed the part with the hump and we fitted it with the lower degree of the Fourier series. In this case, it was a 5th degree. And then we subtracted both models from each other. And the difference is depicted here. You see this large peak, which denotes to the position of the hump on the light curve. Then we obtain through Gaussian fitting of this difference the amplitude, which in our study we selected as the sort of the metric for the prominence of this shock. For the bump, we used a similar approach, but we since we would remove quite a large portion of the light curve, we selected a linear fit between the first and last point of the bump region, and then subtracted again the Fourier series from the linear model, and we got this bell-shaped light curve. And again, selected the amplitude as the metric for the strength of the bump. Now, when we look at the results, we try to first look at the sort of from the educational point of view, the period amplitude plane, the Bailey diagram, the basic plot for the LRS stars. We found differences between stars that show actually a hump feature and those that don't. They lie in the different portions of the period amplitude diagram. You see that when you look at the stars with the large amplitudes and small pulsation periods, those stars have very little hump at all. But as you start moving towards slightly longer pulsation periods and lower amplitudes or below average amplitudes, these stars have shown quite prominent hump in their light curves. But when we reach a certain amplitude in the I band, which was the OGLA observations, we find that the low amplitude LRS stars pulsating in a fundamental mode, they don't show any hump at all. In the bump, the situation is slightly different. The stars with large amplitudes and short pulsation periods, or on average shorter pulsation periods, show quite prominent bump. But as we move toward the longer pulsation periods and lower amplitudes, the bump feature slowly disappears, and we don't see it in the light curve that much. This is a sort of a summary plot of those two previous ones that on the other hand, shows on the x-axis the prominence of the hump, and on the y-axis the prominence of the bump. And the colors are denoting the amplitude of the changes, and the size of the points is connected to the pulsation periods. We see that if we go from the very small humps, stars with the very small humps, the bump is on an average, and these stars have very short pulsation periods, and based on the color you can see that they have also quite high amplitudes. And as we start moving toward sort of average size amplitudes and pulsation periods, the prominence of the bump decreases, and there's all increases, sorry, and you can also find quite prominent hump. But as you start moving toward the low amplitudes and short pulsation periods, or on pretty much all of the pulsation periods, but small amplitudes, these stars have very little effect shown by the hump and bump on the light curves. When we look at the Fourier coefficients and pulsation properties of these stars, we see that the RT, which denotes in these plots the rise time, basically the time that the star needs to take from the pulsation minimum to the pulsation maximum, which is usually quite short. The stars with the short rise time and reasonably high amplitudes have very prominent bump, while the stars that take their time before they reach the pulsation maximum, those do not have very prominent bump. If you look at the Fourier coefficients phi31, R31 on the bottom part, these phi31 coefficient is especially important when we calculate the metallicities, the photometric metallicity of irregular stars. If you're wondering why there are these two sort of hooks here, I refer to our paper from 2019 about the Osterhof groups in the galactic bulge. But for the bump prominence, sort of both photometric Fourier coefficients are similarly, or both Osterhof groups are similarly affected by the prominence of the bump. But if we look at the hump, slightly more affected by the hump are the Osterhof type 2 stars. But that's very negligible and probably not that much significant. These are correlation coefficients between the prominence of the hump in this column and prominence of the bump, with various Fourier coefficients and pulsation features. You see reasonable or halfway significant correlation between the pulsation period and phi31 coefficients between the bump and hump, or anti-correlations. And this is particularly important for the metallicity estimations in irregular stars from their photometric light curves. But as I will
2 minutes left.
2 minutes left.
3
Thank
minutes.
you. 3 minutes. As I will show you later, this actually is not that much, or as I will get back to it later, this is not that much prominent. Since we had distances also for these stars, and we had somewhat estimated reddening toward the galactic bulge irregular stars, we decided to plot also the color magnitude diagrams, where on the left panel you see the color magnitude diagram for the bulge irregular stars from our study, and color-coded is based on the prominence of the hump. You see the stars with the most prominent hump are more concentrated along the red edge of the instability strip, while the stars with very little prominence of the hump are more closer to the blue edge. And also the stars with the more prominent hump are slightly more brighter than their less prominent counterparts. For the bump, it's slightly reversed. We see that the stars with the most prominent bump are in the central region of the instability strip, and stars with a reasonable prominence of the bump are more close to the blue. While on the red side, we don't see that much stars with a very prominent bump. But here is a sort of a problem. The distances and the reddening were calculated using the photometric metallicities for these stars. So there is some introduced correlation and degeneracy between the pulsation properties and the colors and the reddened magnitudes. But we don't detect any correlation with the photometric metallicities and the prominence of these features. So it's kind of a puzzling thing. And I guess unless we start using Gaia for the nearby irregular stars, we won't know for sure, because there's a lot of things that going on that are actually connected to each other. But in the end, I would just want to believe. So to summarize, we used the photometry from the OGLAS survey for the galactic bulge to study the effects of the main and early shock on the fundamental mode irregular stars. In the Bailey diagram, these stars show prominence for the hump, that these stars are located in the lower amplitude regime, while the stars with prominent bump regimes have average and above average amplitudes. in the column magnitude diagram, we see some sort of a dichotomy, but unless we start using a different source of distances, we cannot be actually sure. I referred to our paper from 2020. There's more of it. I could not put it in all in 15 minutes, but thank you for your attention. And happy birthday to George Preston.
So much. Okay, questions from Zdenek. Yeah, I think that's just.
Have you compared your strong and weak bump and humps to, say, the spectra from George and Chris's survey of the RLRs to see that the emission line strengths correlate with your light curve bump and humps?
In this study, we used the bulge RLR stars. Those were not covered in their spectroscopic survey. It's an obvious thing to do right now, since the data is public and there is a quite well described light curves for the nearby RLR stars, either from Kepler or from TESS. I just have to wait for perhaps Laszlo Molnar and his team to process the TESS data, and then I can start looking at the spectra from George Preston and Chris Needham. But it's an obvious path to do right now.
Okay, we have an online question from Horace. Horace, please go ahead.
Hello, very interesting. If you are looking at a RRAB star that is not modulated, does the bump repeat very precisely from one cycle to the next?
For the non-modulated stars?
Correct.
For the non-modulated stars, I didn't see changes in the bump. If I don't look at the Blaschko, if I look only on the non-modulated non-Blaschko stars, I don't see changes in the bump. But if I look at the modulated stars, I see some changes in some stars, in modulated stars. But that's again another project on its own.
Okay, thank you.
I also have a question. So it seems like this is already a pretty big sample in which you detected the humps and bumps. Kind of what do we need to understand why they appear more strongly in some of the stars rather than others, to get a more physical picture of what's happening?
I guess I would say that we need to understand the physics, and yeah, I guess we need to understand and model the physics behind the shocks, I think. Or what I think was suggested in one of the papers by George Preston, that we should look at maybe omega Cen, where we have different populations of RLR stars, and do the spectroscopy, and the light curves for omega Cen are, I would say, already there with the precision that we could do this kind of analysis. We could get a little bit more deeper understanding about that, but we would have to have also spectra for those stars, like in a way that was done by George Preston in his papers.
And here's a question from George.
I would just like to comment that there is a profound metallicity effect. The high metallicity RLR stars have barely detectable hydrogen and helium emission in the samples that I had available to me. So there is a pronounced abundance effect that you need to find somehow.
Yes, I have a comment on that as well. That I think that was in your paper from 2022. There will be a talk by Andrea Kunder, I think in a couple of hours. She will talk about the chemodynamics of the RLR stars in the bulge. There was a relation by Wallerstein 2011, I think, for the calcium line and the metallicity, and she will talk about that. And when I looked at the correlation between the photometric metallicities and these prominent features, I didn't find any correlation. But when I would use what she will be talking about, perhaps the different relation or the relation for the calcium and the prominence of the hump, I could see a correlation. But it's something that I did like 2-3 weeks ago. I looked at it and I saw a semi-strong correlation between the metallicity from the calcium and the strength of the hump. So I think that the photometric metallicity might not be the good path for checking this, but spectroscopic will be definitely good ones.
Yeah, just to follow up on that. So spectroscopic metallicities of bulge aurolari stars are difficult. And so we rely oftentimes on the photometric metallicities, which aren't going to be as good as yours, George.
Great. Thank you so much for the discussion. And let's thank Zdenek again.
Thank you for inviting me.